Section 15.8, Integrals in Spherical Coordinates. The spherical coordinates rho, theta, phi of a point P in space are shown in the figure, where rho is the distance from O to P. So that's the distance from the origin to some point P. So over here is rho. Phi is the angle between the positive z-axis and the line segment OP. So phi is this angle. And note that rho is always going to be greater than or equal to 0, and because of the distance. And phi is always going to be between 0 and pi. So we're basically coming up with this system in order to try to trace out spheres. So what we do is we take, like, you could think of this like as a stick tracing out as it rotates around. So what it does is it rotates up and down. So it traces out all of these points, and it traces out all of these points. And then after it finishes tracing out all of those points, what we do is we take this kind of semicircle that we have now, and we rotate it around. So we kind of go around like this, 180 degrees, and that's where we rotate around theta. So rho is used to be the radius of our sphere, phi is used to draw our kind of semicircle, and then theta is used to rotate our semicircle around to get a three-dimensional sphere out of it. So notice that you have theta going around 180 degrees because you want to rotate all the way around to get the sphere built up, but you only have phi rotating around 180 degrees because you only want a semicircle when you rotate it. If you would rotate phi all the way around 180, then you'd end up rotating this half and rotating this half, and you'd end up with like a double sphere. You'd count everything twice. Kind of like when we did our solids of revolution, we would only rotate around one half of whatever we were, like one little cross-section slice, and then rotate around, it would fill up the other side. So we would like to figure out what x, y, and z are in terms of rho, theta, and phi, so that we can convert back and forth from spherical coordinates to rectangular. So what we do is we start with our polar coordinates, theta and r. So we have theta as this angle that comes out, r is this radius, and notice that in polar coordinates we have x equals to r cosine theta and y equals to r sine theta. So we would like to get rid of r though because we only have rho, theta, and phi. So let's see if we can write r in terms of rho, theta, and phi. So to do that, notice that if we go up to the point P that we're trying to trace out to, where rho is the distance from O to P, then we have the angle phi is the same as it is between the z-axis and rho, where it's the angle between rho and the line we draw up to our point from r. So that means that we can rewrite r in terms of this angle phi, because rho is the hypotenuse of a triangle that we make out of that, and r is going to be the opposite side. So that means that the sine of phi is equal to opposite over hypotenuse, that's r over rho. So we have sine of phi equals r over rho, so that means multiplied by rho, we get rho sine phi equals r. So instead of r cosine theta, we have rho sine phi cosine theta. And instead of r sine theta for y, we have rho sine phi times sine theta. So then all we have to do now is figure out what z equals in terms of rho and theta and phi. So we draw another triangle, and we see that if this is the angle phi, then z is adjacent to phi, where rho is still the hypotenuse. So that means that we have cosine of phi is equal to adjacent over hypotenuse, that's z over rho. So again, multiply both sides by rho, you get rho cosine phi is equal to z. So now we have all of these guys in terms of rho, phi, and theta. So that means to convert from rectangular spherical coordinates, we can plug that in for each of those coordinates, but we can also use the equation x squared plus y squared plus z squared equals rho squared, because remember, we have rho as the radius of a sphere. let's do an example with our new coordinates. How about we try to take the point 2, pi over 4, and pi over 3 and plot it. So let's draw our axes. Say here's z, this could be x, and here's y. So what I want to do is I want to rotate pi over 4. Remember, that's the same theta from polar. So I can do that in the xy plane. So I'll rotate pi over 4. So that's like over here. Now I'll draw this first. So that's our pi over 4 rotation. And I want to make sure that I go pi over 3 rotated down from the z-axis. Oh, I wrote y twice. I need a z over there. So let's say here's the pi over 3 rotation. And it's got to be a distance 2 for rho. So that kind of lies above this thing over here. So maybe I could draw it something like this. So here's our point over here at 2 pi over 4 pi over 3. So let's see what this corresponds to with rectangular coordinates. So we have x equals r cosine theta, where r is rho sine phi. So we have rho sine phi cosine theta. And that's equal to 2 times the sine of pi over 3 times the cosine of pi over 4. So that's equal to 2 times the square root of 3 over 2 times 1 over the square root of 2, which is the square root of 3/2. Then our y-coordinate is r sine theta, so that's rho sine phi times sine theta. And that's 2 times the sine of pi over 3 times the sine of pi over 4. So that's 2 times rad 3 over 2 times 1 over rad 2. So again, it's the square root of 3/2. Now let's get z. So that's rho cosine phi. It's the only one that takes cosine phi and doesn't have any theta, because remember in cylindrical coordinates we didn't even have theta with z, we just had z. So this is 2 cosine pi over 3, and that's 2 times 1/2, which is 1. So our point is square root of 3/2, square root of 3/2, 1 in rectangular coordinates. Just a heads up, by the way, in physics sometimes the roles of phi and theta are switched, and sometimes they just write r instead of rho, just because it's a radius anyway. They just use the same r for every different radius, whether it's be a sphere or a circle. So you have to be a little bit careful of the different context you're using to make sure that even though the coordinates are always going to be the same, that you're using the right notation. Okay, so what if we have a point given in rectangular coordinates? Let's find spherical coordinates for it. So we have rho squared equals x squared plus y squared plus z squared, so that means we could solve for rho as the square root of x squared plus y squared plus z squared. So that's going to be the square root of 0 plus 12 plus 4. So that's just 4. Square root of 16 is 4. Let's see, we have cosine phi is equal to z over rho, because rho cosine phi equals z, or as we've said. So that means that negative 2 over 4, and that's negative 1/2. So taking cosine inverse both sides, we see that phi is equal to 2 pi over 3. All right, how about theta? We have cosine theta is equal to x over rho sine phi. But that's just 0, because our first coordinate was 0. So that means that theta must be pi over 2. Notice that even though theta equals 3 pi over 2 also results in cosine theta being 0, there's no way that theta could be 3 pi over 2, because in this case y is 2 rad 3, which is greater than 0. So we have to have y positive, so that means it must be over here and not over here. So our point is therefore in spherical coordinates 4 pi over 2, 2 pi over 3. Really, our whole point of learning about spherical coordinates was to do triple integration in spherical coordinates. So let's see if we can find a way to do that. What we do is we draw a typical kind of spherical wedge, and then we try to take that volume of the wedge, dv, like that, and we see what that is. So we, similar to the way we did in polar coordinates, we kind of get a r d theta, but in this case, remember, r is rho sine phi, and then dr would be d rho. So instead of r d theta, we have rho sine phi d theta d phi, but then we need this also in 3D. So we also have this change in phi times rho to accommodate for this dimension for our volume over here. So we have one extra rho thrown in, and we have d phi. So that means that instead of rho sine phi, we have rho squared sine phi. Instead of, r dr d theta, we have an r times a rho, so it's rho squared sine phi, and then we have d rho d theta of d phi. Notice this is just the x coordinate. We already said x is r cosine theta, so that's rho sine phi cosine theta. We said y was r sine theta, so that's rho sine phi sine theta. And then we said z was rho cosine phi, so that's just the z. So let's evaluate this triple integral, where b is the unit ball. So because we have a sphere, this is a very classical spherical integral problem. So we'll rewrite our b using spherical coordinates. So that'll be all of the rho theta phi's such that it looks like our radius goes from 0 to 1, because it's all this thing less than or equal to 1. And it looks like our theta goes from 0 to 2 pi to trace all the way around the circle. And then, as usual, building the semicircle that we're going to rotate around, we only need to go to 180 degrees. So that means that phi only goes up to pi. Okay, so that's our unit ball. Remember, we also have that x squared plus y squared plus z squared is rho squared, because rho is the radius of our sphere. So that means that our triple integral over r of e to the x squared plus y squared plus z squared to the 3/2 dv becomes the integral from 0 to pi, integral from 0 to 2 pi, the integral from 0 to 1, e to the rho squared to the 3/2, and then rho squared sine phi d rho d theta d phi. So we have our rho function separated from our phi function, separated from our theta function, so we can write this triple integral as 3 single variable integrals multiplied together. So we get the integral from 0 to pi of sine phi d phi And we have the integral from 0 to 2 pi d theta. And we have the integral from 0 to 1 rho squared e to the rho cubed d rho. So all of these are fairly easy to evaluate. We have minus cosine phi for our first one. We go from 0 to pi, and then from 0 to 2 pi d theta is just 2 pi. And then our last one, notice this is only easy because of the rho squared in there, which gives us a very obvious mental u substitution. Just let u equal rho cubed, and then you have 3 rho squared. So we just multiply by 1/3 to compensate for that. So we get 1/3 e to the rho cubed from 0 to 1. So that just works out to 4/3 times pi times e minus 1. Notice that if you had wanted to write this using rectangular coordinates, then this integral would have been the integral from -1 to 1 from minus the square root of 1 minus x squared to the square root of 1 minus x squared. And then your inner integral will be the worst one, from minus the square root of 1 minus x squared plus, or minus y squared, because that's, z, or the bottom half of z, and then you get the top half of z, which is not very pleasant. You still have this really unpleasant thing inside, e to the x squared plus y squared plus z squared to the 3/2, and then you go dz, dy, dx. Way easier to just use spherical coordinates when you have a sphere. Let's now use spherical coordinates to find the volume of the solid that lies above the cone, z equals square root of x squared plus y squared, and below the sphere, x squared plus y squared plus z squared equals z. So we have, let's see if we can do this in spherical coordinates. We have x squared plus y squared plus z squared equals c. So that means that in spherical coordinates, this is just rho squared, and then z is just rho cosine phi. So rho must equal rho cosine phi. So dividing by rho, we get that rho is equal to cosine phi. So that's the equation of our sphere in spherical coordinates. Okay, how about our cone? So our cone is z equals square root of x squared plus y squared. So in spherical coordinates, z is rho cosine phi. And then the square root of x squared plus y squared is a mess. So that's the square root of, let's see, x is rho sine phi cosine theta. So when I have to square that, I get rho squared sine squared phi cosine squared theta. And then for y, I get rho sine phi sine theta, so I square that, and I get rho squared sine squared phi sine squared theta. And that's actually not too bad though, because notice I have rho squared sine squared phi in both, so I factor that out, and what's left is cosine squared plus sine squared, which is 1. So it's 1 times rho squared sine squared phi. Take the square root, that's just rho sine phi. So it actually wasn't too bad. So that means that z is, or rho cosine phi is equal to rho sine phi. So canceling out rho, I see that cosine phi is equal to sine phi. So that tells me that phi must rotate out until pi over 4. Remember, we won't take phi to be in the third quadrant, where the other point where cosine and sine are equal, because we only take phi up until pi, only take it up until 180. So what this means is that we trace out our sphere until we get to pi over 4 in the picture, and then we stop. Because if we were to keep going past pi over 4, we would keep tracing out the sphere, and we don't want to do that. We only want to trace out the sphere up until we get to the cone. So that means that's all we're going to integrate until. So we can now write our region E using spherical coordinates. So that'll be all of the rho, theta, phis, such that theta has to rotate all the way around to get our sphere. So that'll be between 0 and 2 pi. Then phi only goes up until pi over 4 because it's a stop for our cone. So phi goes from 0 to pi over 4. And then rho has to go from 0 to our sphere, which we said is rho cosine phi. So that's where rho stops at. So you can imagine that first, when we integrate with respect to rho, we're kind of drawing some point over here. The integral stacks up all these little pieces until we get this line segment. And then what we do is we integrate with respect to phi. So we move up and down until we get to pi over 4. So you can imagine stacking up all of these little guys as we rotate until we get to pi over 4. So we end up with this like slice over here. So this slice fills in as we integrate first with respect to rho and then with respect to phi. Then we finish our triple integral by integrating with respect to theta, and we rotate all the way around. So what we do is we rotate like this, and our little slice fills up this volume. So that's what's going on here. We'll first integrate with respect to rho, then phi, and then theta, and we'll fill up our volume. So the volume of our region E will be the triple integral over E of 1 dV, as we've seen. So when we convert to spherical coordinates, we get from 0 to 2 pi for theta, 0 to pi over 4 for phi, and then 0 to cosine phi for rho. And that'll be dV is rho squared sine phi, d rho, d phi, d theta. So notice that the d theta integral can easily be separated out. So let's do that first. We've got 0 to 2 pi d theta, because there's no thetas in here. And we'll have 0 to pi over 4 for phi. We could just do this integral with respect to rho really quick. Sine phi will be constant with respect to rho. So we just have rho cubed over 3 evaluated from rho equals 0 to rho equals cosine phi d phi, and that's just 2 pi over 3 times the integral from 0 to pi over 4 sine phi cosine cubed phi d phi, which is 2 pi over 3 times minus cosine to the 4th phi over 4. Quick substitution, and we do that from 0 to pi over 4, and we just get pi over 8.